Look up at the night sky for a moment. Even if you live in a bright city and you can only see a few stars, you are still looking into a place that is so large your mind cannot fully hold it. That place is the universe. It is not just a collection of stars. It is the whole stage. Space, time, matter, energy, light, gravity, and the laws that make reality behave the way it does. Everything you have ever touched, every person you have ever met, every sound you have ever heard, every thought you have ever had exists inside the universe. There is no known outside. The universe is the ultimate container. A simple way to start is this. The universe is old. About 13.8 billion years old. That number is hard to feel, so let us shrink it. Imagine the entire history of the universe is one single calendar year. In that calendar, the universe is born at midnight on 1st January. The Milky Way forms around September. The Sun and Earth appear around early December. Dinosaurs appear around Christmas week. Modern humans show up only in the last hour of the last day, and all of written history is less than the final minute. That is how late we arrive in the story. We are new. The universe has been running its processes for an unimaginably long time. So what happened at the start? Many people picture the Big Bang as an explosion in empty space, like a bomb going off. That image is not quite right. The Big Bang was not an explosion in space. It was the expansion of space itself. If you want an image, imagine the surface of a balloon with dots on it. The dots are galaxies. As the balloon inflates, the dots move away from each other, not because they are traveling across the surface, but because the surface itself is stretching. In a similar way, space expanded. The universe grew from a hot, dense state into a larger, cooler state. This expansion is still happening today. In fact, it seems to be speeding up. In the earliest moments, the universe was so hot that matter as we know it could not exist. There were no atoms. There were not even stable protons and neutrons at first. It was a storm of energy and tiny particles flashing in and out. As the universe expanded, it cooled. When it cooled enough, particles could stick together more reliably. Protons and neutrons formed. Then, a little later, the first simple atomic nuclei formed, mostly hydrogen and helium. But even then, there was no light traveling freely. The universe was like a dense fog. Light could not move far because it kept bouncing off charged particles. After about 380,000 years, the universe cooled enough for electrons to attach to nuclei, forming full atoms. This changed everything. The fog cleared. Light could travel long distances. That ancient light still exists today. It has been stretched by the expansion of space, so it is no longer visible light. It is microwave light. We call it the cosmic microwave background. It is like a baby photo of the universe. It is one of the strongest pieces of evidence that the universe began in a hot, dense state. Now here is the next part of the story. Gravity. Gravity is the sculptor of the universe. It is the force that pulls matter together. If you have ever watched rain collect into puddles, you have seen a simple version of what gravity does. It gathers. In the early universe, matter was not perfectly smooth. There were tiny differences in density. Some areas had slightly more matter than others. Gravity pulled harder in those areas, attracting more matter, making them even denser. Over time, those dense regions became the seeds of everything large. Stars, galaxies, and clusters of galaxies. For a while, the universe had no stars. This period is sometimes called the Dark Ages. It was filled with gas, mostly hydrogen, and it slowly gathered into clouds. When a cloud became dense enough, gravity squeezed it tighter and tighter. As it collapsed, it heated up. If it gathered enough mass, the center became so hot and so pressurized that nuclear fusion started. That was the birth of the first stars. A star is not a ball of fire. Fire needs oxygen. Space has almost none. A star shines because of fusion. In the core of a star, hydrogen nuclei are forced together to make helium. This process releases energy. That energy tries to push outward. Gravity tries to pull inward. A star is a balance between these two. Push from fusion, pull from gravity. That is why a star can stay stable for millions or billions of years. Our sun is one of these stars. It is about 4.6 billion years old. It is roughly halfway through its life. It is not special in size or brightness. That is a useful fact. If our sun is ordinary, then ordinary stars may commonly have planets. And if planets are common, then the ingredients for life may also be common. Stars do more than shine. They build the elements. At the start, the universe mostly had hydrogen and helium, but you and I are made of much heavier elements. Carbon, oxygen, nitrogen, calcium, iron. Where did those come from? They were made inside stars. Stars are element factories. As stars age, they can fuse heavier and heavier elements in their cores, up to iron in the most massive stars. When massive stars die, they explode as supernovae. In that explosion, even heavier elements are formed, and the star's material is thrown out into space. That material becomes the raw stuff for new stars, new planets, and eventually people. This means something simple and powerful. The atoms in your body were cooked inside ancient stars. You are not separate from the cosmos. You are a piece of it. Let us zoom out. Stars gather into galaxies. A galaxy is a huge system of stars, gas, dust, and dark matter held together by gravity. Our galaxy is the Milky Way. It is a spiral galaxy. If you could see it from the outside, it would look like a glowing pinwheel. The Milky Way contains hundreds of billions of stars, and it is not alone. The observable universe contains hundreds of billions of galaxies, maybe more. Each one is a city of stars. When we say observable universe, we mean the part we can see, because light from there has had time to reach us. The universe is 13.88 billion years old, but the observable universe is much larger than 13.8 billion light years across. That sounds strange until you remember expansion. While the light was traveling, space was stretching, so the distance to the farthest visible regions has grown. The observable universe is about 93 billion light years across. Beyond that, there may be more universe. Perhaps much more. Possibly infinite. We do not know. Our view is limited by the speed of light and the age of the universe. Now, inside a galaxy, stars are not spread evenly. They form in regions with more gas. They also move. The Milky Way rotates. Our solar system is orbiting the galactic center. One orbit takes about 225 to 250 million years. That means since dinosaurs first appeared, our solar system has only completed about one full orbit around the Milky Way. That gives you a sense of scale. At the center of the Milky Way, there is a supermassive black hole. Most large galaxies appear to have one. A black hole is one of the strangest objects in the universe. It forms when a massive star collapses under gravity at the end of its life. If the core is heavy enough, nothing can stop the collapse. Not pressure, not heat, not even the normal behavior of atoms. The matter collapses into an incredibly dense region. Gravity becomes so strong that there is a boundary called the event horizon. Cross that boundary and you cannot get back out. Not even light. Black holes are often misunderstood. They do not roam around eating everything. If the sun were replaced by a black hole with the same mass, Earth would keep orbiting in the same way. The gravity would be the same at our distance. The danger comes from getting too close. Most of space is far from black holes, so they are not a daily threat. But they are important for physics because they push the laws of nature to extremes. Black holes also teach us about time. According to Einstein's general relativity, gravity is not just a force pulling objects. It is the bending of space and time. Massive objects bend space-time like a heavy ball bending a trampoline. This bending affects how objects move. It also affects how time passes. The stronger the gravity, the slower time moves, compared to a place with weaker gravity. This is not a philosophy idea. It is real. It is measured. Even GPS systems need to correct for time differences due to gravity and speed, or they would drift and become useless. So the universe is not just space full of objects. It is space and time together, shaped by matter and energy. That is the big picture view of relativity. Now let us talk about something that sounds like science fiction, but it is part of mainstream cosmology: dark matter and dark energy. These two words show up a lot, and they can sound like mysterious magical stuff. They are not magic. They are names for effects we observe but do not fully explain yet. Dark matter is called dark because it does not emit light. We cannot see it with telescopes, but we can detect its gravity. For example, galaxies rotate. If you measure how fast stars orbit the center of a galaxy, you can calculate how much mass is needed to hold them in orbit. When scientists did this, they found a problem. The visible matter was not enough. There had to be extra mass we could not see, otherwise galaxies would fly apart. That extra mass is what we call dark matter. Dark matter also helps explain the structure of the universe. It acts like an invisible scaffolding. Normal matter, like gas and dust, falls into the gravitational wells created by dark matter, helping galaxies form. Without dark matter, the universe would look very different. So dark matter is not a small detail. It is a major player. Yet we do not know what it is made of. Many ideas exist, but no final answer yet. Dark energy is even stranger. When scientists measured how fast the universe is expanding, they found that the expansion is speeding up. This means something is pushing space to expand faster over time. That pushing effect is called dark energy. It could be a property of space itself, like a vacuum energy, or it could be something else entirely. Again, we do not have a complete explanation, but we can measure its effects on the expansion of the universe. Now, here is a simple truth. Everything you can see, every star, every planet, every cloud of gas, every human, every atom of your body makes up only a small fraction of the universe's total content. Most of the universe is dark matter and dark energy. In other words, the universe is mostly something we do not yet understand. That is humbling. It means we are still early in our knowledge. We have learned a lot, but we are far from done. Let us come back to planets and life, because this is where people feel the story most personally. Planets form around young stars from the leftover material in the star-forming disk. Some planets become rocky, some become gas giants, some become ice worlds. Our solar system has a bit of everything, but for a long time we did not know if other stars had planets. We guessed they did, but we had not proven it. Now we have discovered thousands of exoplanets, planets around other stars. Many are very different from our planets. Some are hot giants close to their stars. Some are rocky worlds larger than Earth. Some orbit two stars, like something out of a film. This tells us that nature is creative. The solar system is not the only way to arrange planets. The big question is life. Is life common? Is intelligent life common? We do not know, but we can think clearly about what life needs, at least life like ours. It needs energy, chemistry, and a stable environment for long enough to develop complexity. Water is useful because it is a good solvent for chemistry. It allows molecules to mix and react. That is why scientists often look for liquid water when searching for life. But life could possibly exist in other forms, using other liquids. We must be careful not to assume Earth is the only template. Even on Earth, life is extremely adaptable. It lives in deep ocean vents with no sunlight, using chemical energy from the Earth itself. It lives in acidic pools. It lives in freezing ice. It lives in hot springs. This tells us that life can find a way in harsh conditions. So when we think about life elsewhere, we should keep an open mind. When we search for life in the universe, we use several methods. We look for exoplanets in the habitable zone, the region around a star where temperatures might allow liquid water. We study the atmosphere of exoplanets when possible, looking for gases that could be signs of life, such as oxygen, methane, or unusual mixtures that are hard to explain by geology alone. We also listen for radio signals in case an intelligent civilization is broadcasting. This search is called SETI, the search for extraterrestrial intelligence. So far, we have not found a clear signal, but the search has barely begun in cosmic terms. The universe is vast, and we have only looked at a tiny fraction of the possibilities. Now let us talk about how we know what we know, because this is important. The universe is far away, and we cannot visit most places. So how can we learn about it? We learn through light, and more broadly, through information carried by waves and particles. Light is not just what your eyes see. Light comes in many forms: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. These are all the same kind of thing, electromagnetic radiation, but with different energies. Different objects in the universe emit different kinds of light. Cold gas clouds emit radio waves. Warm objects glow in infrared. Hot stars emit visible and ultraviolet. Violent events like supernovae and black hole jets can emit X-rays and gamma rays. By using telescopes that can detect different types of light, we build a more complete picture. When you see a photo from a space telescope, you might see false colors. That does not mean it is fake. It means the telescope is detecting light your eyes cannot see, like infrared, and scientists map that data into visible colors so we can understand it visually. It is like translating a sound into a picture. The data is real. The colors are a human interpretation tool. Light also carries fingerprints. When light passes through gas, certain wavelengths are absorbed, creating dark lines in a spectrum. These lines tell us which elements are present. This is how we know what stars are made of, even though we cannot scoop a piece of star into a lab. We read the light. Light also tells us about motion. When an object moves away, its light shifts toward the red end of the spectrum. This is called redshift. When an object moves closer, the light shifts toward blue. By measuring redshift, we can tell how fast galaxies are moving away from us. This is one of the key ways we discovered that the universe is expanding. Now, here is another mind-bending fact. The faster a galaxy is receding, the farther away it usually is. This is called Hubble's law. It is strong evidence that the universe expanded from a denser state. In other words, if you reverse the expansion, you get a time when everything was closer together. But the universe is not just smooth expansion. It has structure. Galaxies group into clusters. Clusters group into superclusters. There are huge filaments of galaxies with vast empty regions between them called voids. The universe looks like a cosmic web. It is like foam, with bubbles of emptiness and walls of matter. This structure comes from gravity amplifying tiny differences over time, helped by dark matter. Let us zoom down again to our solar system because it is the place we know best. The sun provides energy. That energy powers weather, oceans, and life. Earth has a magnetic field that helps protect us from harmful solar particles. Earth also has an atmosphere that traps heat and supports life. These features make Earth habitable, but Earth has not always been stable. It has had mass extinctions. It has been hit by asteroids. Its climate has shifted dramatically. Life survived through resilience and adaptation. Mars is a good example of how a planet can change. Mars today is cold, dry, and thin in atmosphere. But evidence suggests that long ago Mars may have had liquid water on its surface. Rivers, lakes, maybe even a shallow ocean. Over time, Mars lost much of its atmosphere. Without a thick atmosphere, it could not keep warmth. Without a strong magnetic field, the solar wind could strip gas away more easily. Mars became the cold desert world we see now. Studying Mars is like looking at an alternate history of what could happen to a planet. The moon also holds clues. It has no atmosphere, no weather, no erosion like Earth. Its surface is like a fossil record of impacts. It shows us what the early solar system was like when collisions were common. The craters are scars from a violent past. Asteroids and comets are leftovers. They are the building blocks that never fully became planets. They carry ancient material. Some may have delivered water and organic molecules to early Earth. We are still learning how important they were. in the origin of life. Now let us go back to the deep universe and ask a harder question. What is the universe made of at the smallest level? We talk about atoms, but atoms are not the end. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. Quarks are held together by the strong nuclear force. There are also other particles, like neutrinos, which pass through matter easily. There are photons, particles of light. There are many more. All of this is described by a framework called the Standard Model of Particle Physics. The Standard Model is powerful. It predicts many things accurately, but it is not complete. It does not include gravity in the same way. This is one reason physicists search for a deeper theory that unites quantum physics and gravity. Quantum physics is the physics of the very small. It is strange because it does not match everyday intuition. In quantum physics, particles behave like probabilities until measured. They can be in a mix of states. They can act like waves and particles. This is not just a curiosity. It is the basis for modern technology like semiconductors and lasers. Relativity is the physics of the very large and the very fast. It tells us that space and time are connected. It tells us that the speed of light is a cosmic limit for information. It tells us that mass and energy are linked. It tells us that gravity is geometry. The problem is this. Quantum physics and relativity both work extremely well in their domains, but they clash in extreme conditions, like the center of a black hole or the earliest moments of the universe. This is why the universe is still a frontier. The laws are not fully unified. Now let us talk about the future of the universe, because it is both fascinating and unsettling. If the expansion continues forever, galaxies will move farther apart. Over time, distant galaxies will drift beyond what we can see. The night sky in the far future will be emptier for observers in any one galaxy. Stars will gradually burn out. Star formation will slow as gas runs out. Eventually, the universe could become a cold, dark place with dead stars, black holes, and faint radiation. This idea is sometimes called the heat death of the universe. But there are other possibilities. The expansion might change. Dark energy might not be constant. The universe might tear apart if expansion accelerates too strongly, ripping galaxies, stars, planets, and even atoms. That idea is called the Big Rip. Or the expansion might slow in reverse, leading to a collapse called the Big Crunch. Or the universe might go through cycles. We do not know which is correct. Current evidence suggests continued expansion, but the deep nature of dark energy is unknown, and that leaves room for surprises. Now here is the personal part. When you hear all of this, you might feel small. That is normal. But small is not the same as meaningless. The fact that we are small makes it more impressive that we can understand anything at all. The universe has produced beings that can ask questions about the universe. That is not nothing. Think about what you are doing when you learn astronomy. You are using atoms forged in stars to think about stars. You are using a brain built by evolution on a small planet to model galaxies and black holes. That is like a wave in the ocean becoming aware of the ocean. It is one of the strangest facts of reality. People sometimes ask, why is the universe so big? Why is it so old? Why does it have laws at all? Science can answer many questions, but not all. Science is a method. It is the method of making careful observations, building models, testing them, and correcting errors. It works because the universe is consistent. The same laws apply in Singapore as they do on the far side of the Milky Way. That consistency is what makes knowledge possible. But some questions might be deeper than measurement. Why is there something rather than nothing? Why do the laws have the form they do? Are there multiple universes? Did the universe have a cause? These are questions where science and philosophy meet. Science can sometimes push into them, but it might not answer them fully. That does not mean the questions are useless. It means we must be honest about what we know and what we do not know. Let us finish by returning to the night sky. When you look up, you are seeing more than beauty. You are seeing history. Every star you see is a sun. Many may have planets. The light from them left long ago. Some of those stars might already be gone, and their light is just arriving now. The sky is a time machine. And if you look deeper, with telescopes, you see galaxies. Each galaxy contains more stars than you can count in a lifetime. And beyond those galaxies are more galaxies. And behind all of it is the ancient microwave glow from the early universe. It is like a whisper from the beginning, still present everywhere, still traveling through space. The universe is not quiet. It is filled with motion. Planets orbit, stars spin, galaxies collide, black holes eat and merge. Space expands. Time flows differently in different places. And through it all, the same simple forces shape complexity. Gravity gathers matter. Fusion lights stars. Chemistry builds molecules. Evolution builds life. Intelligence builds questions. We are not the center. We are not the goal. But we are part of the universe's story. We are the part that can reflect. We can look up and say, I want to understand. We can build instruments that see beyond our eyes. We can send probes to other worlds. We can write math that predicts invisible things. We can correct ourselves when we are wrong. That is rare. That is powerful. So the universe is not just a distant place. It is your origin and your environment. You live in it every second. It shaped the atoms in your body. It shaped the planet under your feet. It shaped the sunlight on your skin. The universe is not separate from you. It is the bigger reality you are made from. And the most honest ending is this. We still do not know everything. We do not know what dark matter is. We do not know what dark energy is. We do not know if life is common. We do not know if the universe is infinite. We do not know if there are other universes. We do not know the final fate for certain. But we do know enough to say this with confidence. The universe is ancient, vast, and structured. It is driven by simple laws that produce complex outcomes. It can make stars, planets, oceans, and minds. It can make silence and storms. It can make destruction and creation in the same event. And for a short time, on at least one world, it has made a species that can tell the story back to itself.